Hello, class. This, I think, is like my fourth lecture of the day, and it's late. I'm not exactly sure how late it is, but I just had chocolate. So I'm pretty good. Now, what I want to do in this lecture is I want to make sure my microphone is working fine. I want to look at a three-dimensional. Now, this isn't a heavy-duty three-dimensional problem, but it would be I'd love to say it was a metal plate, but the weight of it probably doesn't justify that because it's 4 meters by 4 meters. And I only have it at 200 kilograms, which is about 450 pounds. So, probably not a steel thing, but some type of composite or plywood or something like that. What is 4 meters? 16 feet by, yeah, that would be about, yeah, that'd probably be a sheet of plywood, something like that, a 3/4 inch plywood sheet. Yeah. So anyway, what I've got here is I've got a couple columns that are supporting this. And of course, I've got a weight force that's going down anyway, and we can figure out obviously what the weight force is, and that's not too hard because my weight force is just going to be my mass times my gravitational constant, and that's just 200 kilograms. And I've pretty much drawn this. You can see that there's going to be a force pushing up from column B, and there's going to be another force pushing up from column A. I've just drawn this in sort of a oblique drawing. And then we've got another column C that we're going to put somewhere down here on this 1 meter line, 1 meter off the end of the plate. And that has to somehow balance out these other things so that, and I want to look at three different things. What if I want A and B? So what if I want the force on A? So three things. So the first one is going to be that the force on column A equals the force on column B. All right. The second one is that column B takes all of the weight, right? I'll write that out later because we'll see what I shouldn't say all the weight, but all of the weight that these columns are going to take, because as I said, C is going to be along 1 meter, and you can see these columns are set 1 meter off the end too. So there's going to be we're going to sum moments about that center axis and this axis, and really we're going to do that, but we're also going to sum them three-dimensionally, and it comes out to the same thing, only it's a little more robust notation and everything else. So the first thing we want to do is look at that. And where do we put C? Do we put C over here? Do we put C over here? Where along here are we going to put C? So I'm going to say that this distance right here, right, the distance from the y-axis, because this is my y-axis, y, this is my x-axis, I hat, I put that j hat there, and my z-axis coming up out of the board, right? That's my z-axis. God, can't even draw straight there. And that's my z-axis, or k hat, right? All right. And then you can see that these are set back. These are along this back line here, 1 meter off the back. I've drawn 1 meter. These are all say 1 meter. I hope everybody can see that. 1 meter, 1 meter in between each of these individual marks that I've got down there. So I've got the plate here, and what we want to do is we want to find out where can we do it so that it's maximum stable, and that's so that F sub A and F sub B are going to be the same. And so I want to look at this, but instead of looking at it like this, I sort of want to look at it in from a top view, right? If I look at it from a top view, I'm not going to draw it. I guess I could probably draw it just as wide. Let's see. 2, 4, 6, 8. There we go. So that would be my top view. If I'm looking down, let's say from here, right? I'm looking down from there on the top of the thing. If this, I'm just going to put in my X and my Y axes again. This is my X axis going through right there. And then this would be my Y axis, and the Z axis would be coming up out of the board. And so you can see if we still are marking these off, you know, 1 meter, 1 meter, 1 meter, each of those are 1. I'll just put a 1 there for 1 meter. Oh God, a meter. Anyway, you know what I mean. Each one of those, and I'm just going to mark off 1 meter increments over here too. Now, the first, well, let's say B, because I've called this B and I've called that A. I can put A. Well, I can put A, and A is 1 meter off the back, right there. So that is A. And then B is right here, right next to it. That's B. And then C has to be along this line down at the bottom. Has to be along that line. And of course, here's the origin, right? And where the origin is the center of gravity too, and that's where the weight, that's where my weight force is going to be directed downwards. And these are all working upwards. So I'm figuring that probably C is going to have to be somewhere over here. I don't know where exactly, but I'm going to say that this distance here from that origin on the x-axis to that point right there, I'm going to call that X. I know, really imaginative, right? It's on the x-axis, so I'm going to call it X. You know, sounds good enough to me. So that's going to be the distance where C is going to be located down there. Now, let's just look at the distance vectors to all of these various things. But even before we do that, let's look at these axes here, right? Let's sum the moments about this x-axis right here. So if I'm going to sum the moments about the x-axis equal to 0, and I say 0, why do I say 0? Why do I say that this is 0 there? Because it's not rotating about the x-axis, is it? I mean, isn't that what we're trying to do? We're trying to make sure the thing's not falling or doing anything. So is there rotation about the x-axis? No, there's not. So I can say that all of the sum, if I sum all of the moments about the x-axis, it should be 0. Well, you know, that's going right through the weight. So I don't have to worry about summing the weight in, because any force that goes right through that axis can't create a moment about the axis. And why is that? Because there's no distance vector, is there? The distance vector is 0. So right, well, we can't do that. And so what we do have is we have these two back here. We have F sub A and F sub B. And those are pushing up, so they could cause a moment about this, couldn't they? But how far away are they? They're pushing up, and they're pushing up 1 meter away. So both of those are pushing up 1 meter away. So I could really say F sub A times 1 meter plus F sub B times 1 meter. And then what else do I have here? Now I say that they're positive because they're rotating that in that direction, right? They're tending to push around here in a positive counterclockwise direction around the x-axis, right? And counterclockwise is positive. So if they are doing that, they're both positive. But how about this one, C over here? Now C is 1 meter away as well, right? But C is tending to push it in the clockwise direction. So it would be minus C, or I'll put F sub C, F sub C minus F sub C, that's a minus, times 1 meter. And so you can see if all of that equals 0, then let's divide the whole thing by 1 meter, and that means that F sub A plus F sub Z plus minus F sub C equals 0. So F sub A plus F sub B minus F sub C equals 0, right? Or I could say that F sub C has to equal F sub A plus F sub B. There you go. We know that now. What else do we know? We know that if we sum the forces in the y direction equal to 0, that's going to be F sub A plus F sub B plus F sub C minus W, right? So if we simplify that, we've got F sub A plus F sub B. I'm going to put, parentheses around that, plus F sub C equals W. But we know what W is because W we figured out 200 kilograms, times 9.81 meters per second squared gives us 1960 newtons. All right, actually 1962, is it? I don't know. I'm going to say approximately equals 1960 newtons. All right, so we know that, but we also know something here too, don't we? So we know F sub A and F sub B equals F sub C. So I could really replace this with F sub C and say that that this equals W. Or I could say, just going back here, I could say that 2 F sub C equals W, or F sub C equals 980 newtons. That's a 9. And that implies that F sub A and F sub B equal 980 newtons, and we know that we want F sub A to equal F sub B. So that implies that F sub A equals F sub B equals 490 newtons, right? Does everyone see that? So we know what these are now. We don't know where F sub C is located, though. So what we want to do then, instead of taking, moments about this, why don't we take moments about this now? Because that takes B and W out of the situation, doesn't it? And it just leaves us with C and A, and we already know what A is. A is 490 newtons. So let's do that. Let's sum the moments now about Y. All right, so if I look here, I said that that's going to be X, right? That distance right there. And so if I look, I see that C, whatever C is going to be X distant from that center line that I'm taking the moments about. Now, what's it going to do about this? You know, we're looking from the positive end here. That would be positive. So this C is going to be rotating it in an opposite direction, isn't it? It's going to be rotating in that direction. And what's positive, of course, looking at it from this end would be in that direction. So, because that's the positive Y axis, right? So, if we were looking at it in that direction, this thing would be a negative, right? Because this is pushing up, whereas this one would be a positive. So I'll do that, and I'm just going to put a line underneath this first part that we did, where we found out what F sub A and F sub B are, as well as F sub C, right? Just using our summation of forces and also our summation of moments about the x-axis. I'm going to say axis because I don't want you to think that we took the moment about a point. It's about the x-axis. And so that's what we've got here too. So I've got a C times 1 times whatever x is when I'm summing moments about the y-axis equal to 0 because there's no rotation, no movement at all, right? We have static equilibrium. And that's what I'm using. I'm using the analysis of static equilibrium, right? Summation of the forces in the x and y direction equals 0. Summation of the moments equals 0 about any point or axis. That this is giving me the information that I have. So when I look at this, I see that this is going to be a minus F sub C, and the minus, of course, refers. I should really put the minus on the other thing. I will do that. I'll make that a plus. Then I'll put the minus. Oh yeah, no, x meters, and that should have been a minus if I'm summing the forces about the y-axis. So there we go. It's a minus. All right. Now A is going to be positive. That's also going to be 1 meter away from there. So positive F sub A, right, times 1 meter. I think everybody can see where this is going because that equals 0. So now we know that x sub m is going to be equal to F sub A times 1 meter divided by F sub C, right? And we know what those are already because that's 490 newtons. And I'll just put the 1 meter in there, why not? Divided by 980 newtons. And so that's 1/2, so that would be 0.5 meters. So the distance here now is going to just be 0.5 meters. That's 1 meter over there. That's going to be 0.5 meters. And what that does is that separates them. Now, that was number 1. Now, the second thing is, what if I wanted F sub B to equal 0 newtons? What if I did? Where would I put C? Think about this for a second. I want this to equal 0, right? In fact, why don't I use another color? I wish I had a good color, but I'll just have to use red. What if this was going to be 0 and this was going to be 980? where would I put C then? Where would I put C? Well, if this is going to be 980, 980 divided by 980 is 1 times 1 meter would be 1 meter. So this distance right here, right, for 980, it would be 1 meter over. That's what it would be. Now, if instead, let me use another color here. I don't even know if I've got another really good color. I could use a blue. If instead I wanted B to be 980 and I wanted A to be 0, where would I put it? I would put it right on here, right? I'd put it right on that line there. And then B would be offset by this here. This would be 980, that would be 980. So as I move between these two locations, between here and here, I'm changing the distribution of weight on those two columns that I've got there. And I'm changing the distribution of weight on those two columns by, 980 newtons. Just by moving C from here to here, I'm going to shift all of the weight from this one column all the way to the other column. Do you see what I mean? If I have the weight right here, all of the weight is on A and C. If I have the weight right here, all of the weight is on B and C. But if I have the weight right in the middle, then the weight is going to be evenly distributed between B and C, right? And so you're probably thinking, my God, that's sort of like a Greek temple that they're doing a renovation on, and they're trying to minimize the actual weight on each of the two columns while they're using a temporary support column to hold up the plywood so that they can do the work. Yes, that's true. And this is what you would do. Why? Because you're the smartest guy there. And you're saying, hey, really, if we just, we can sort of shift this right in the middle and then we'll divide that weight evenly between the two. How about that? Should we do that? Now, I've shown you really what I would call the technician's way to, maybe a little more than a technician's way to do this. And that's by looking at the individual axes there. And you know that the axes, there's no rotation about either of those axes, so I could just sum the forces like this. And this is not a very complicated three-dimensional problem, and I'll give you harder three-dimensional problems to do. In fact, the next three-dimensional problem we do probably will be much harder than this and involve cables and weights and everything else. However, what I want to do here is if we look at some of the things that I've got, like the distance between where the weight is located, I'm using the wrong pen, sorry, where the weight is located and point B. Now, do I have all the, yeah, B is, this is A, that's B, or this is B here, that's A, I've got them written here. So the distance to that is going to be 1 meter J hat. Does everyone see that? From here up to here, it's 1 meter. So I'm just going 1 meter J hat. The distance vector from W, I'm going to use these distance vectors to A, right? And A is over here, is going to be minus 1 meter I hat plus 1 meter J hat, right? And then if I wanted the distance vector from W to C, that place that I've got down on the bottom, that would be X meters I hat, right? Minus 1 meter J hat. Does everyone see why it's minus 1? Because I'm going from here down to here, so it's always going to be minus 1 in the Y direction. So those are the individual things, and then the individual distance vectors. And then if I actually looked at the force vectors that I have for each of these of course would only be in the k direction, right? So I would have F sub A, if I wanted to write that. I'm not going to write all of the things out. I'm just going to say that it's F sub A Z in the k direction, and it's pushing up, so it's going to be positive. And then I have F sub B equals F sub B sub Z in the k direction, because of course all the pushing up, and then F sub C is going to be F sub C in the Z direction, and that of course is also k. And if I cross multiply all of these together, I'm going to let you guys, look at all of these and cross multiply all the individual ones. R sub WB is going to be cross multiplied with this J cross K. Let's just draw that here. I love drawing Bjorn Johnston's thing. I, J, K. So if I have J and K, all these are K. J and K is going to give me positive I. And then if I have, for A, minus 1 I times K is going to give me minus J. And then J cross K gives me positive I. So all of these are adding together, and they add up. And then we basically have two different things at the end: the summation in the I's and the J direction. And that gives us the same, that gives us exactly the same thing. I end up getting AY plus, oh wait, excuse me. Yeah, I use different notation in the, sorry, oh, what's going on here? My thing is finally failing me, is it? Okay, so F sub A Z plus F sub BZ equals F sub C sub Z. And that's what we got up here too, F sub A, F sub C. They're only pushing one direction, so I don't know why I really had to put the sub Z on there. We know that they're all going in the Z direction, but what, no, I didn't want to do that. Yeah, I put the Z's on here. So whatever. They're all this. It's the exact same equation I get here when I do it this way using the engineering method of R cross F gives me the moment about a certain point, and using the distance vectors and then the force vectors, it gives me exactly the same relationships that I got up here. And then if I know this, and I then sum all of that, that was the first thing that came out of that. And the second thing that came out of that, let's see, what else do I have? Yeah, the second thing that came out of that was that X in meters is going to be A sub Y times 1 meter, which is exactly the same thing that I got with the other analysis up there, over C sub Y, right? Or F, oh boy, I used the wrong notation again, but there we go. Yes. Okay, F sub C. F sub C and F sub A. F sub A, F sub C, 1 meter, exactly the same thing that I got up there. I don't know why it was so hard for me to write that down. So there you go. Two different ways that we're doing it, and of course, you know, this is the engineer's way, but you know, just looking at it for things like this makes it so much easier. The next thing that we're going to look at is going to be directional vectors, so that we know, for instance, if I have tension in a cable, you know what, the cable is going to be going in a certain direction. It's got tension. So then I can just multiply the tension in the cable times that directional vector and find out what the percentage of, you know, stresses are in the cable and on the supports and things like that. All right. So that's what we're going to try to do next time. That's going to be a three-dimensional problem. And then we're going to start to move on to friction. Actually, we may move on to friction even before we get to that, because this sort of handles that too. I think I'm going to get into friction next. Okay, see you at the next lecture.